Hey everybody, we are talking today a little bit about conversion of energy, right? So in chapter 10 we really sort of set the foundation, introduced these ideas of potential and kinetic energy. This chapter is really about going beyond that, okay? So as we think about things that can change the energy of the system, the change in the energy of the system, so we can talk about changes in kinetic energy. We can talk about changes in potential energy. Those are the two that we've really focused on so far. Now we're going to introduce a few others. So I said at the beginning, it's going to be hard to write down a strict definition of energy. Rather, we're going to introduce it as it becomes necessary. And this is one of those cases, okay? So when we deal with gases, molecules, when we start thinking about what things are doing on a microscopic scale, this is where it becomes important. We introduce delta E thermal. We're going to mess around with that, so think of that as a different term. You can also think about this, delta E, as other changes. Okay, we're going to introduce metabolic energy, okay, as a specific example. And then you want to think about this as being, when I add up all these are affected by any works that are done externally. Okay? We're going to mess around very specifically with this one, and then we're going to think about this one in the context of metabolic energy. Okay? As you start thinking about the concept of efficiency, okay, we're going to think about systems where we want to get something out and we have to pay something. So in a perfect world, the ratio of what you get out versus what you put in would be 1. We get perfect efficiency. The problem is that systems don't behave that way. So while a theoretical efficiency you'd like to be 1, it never happens. Okay? And in fact, in a lot of the typical thermodynamic systems that we're going to work with, or that you might imagine working with, like car engines, the efficiency is really low. It's downward. It's somewhere between 20 and 30%. For most of the power plants, it's somewhere in the range of 30-35%. So think about efficiency as what you get out divided by what you put in. Okay? As you start thinking about the metabolic energy, okay, so we have introduced this notion of mechanical work. Okay? So mechanical work, lifting things up, gravity does work, and you have to do work against that. Well, there's a problem, right? If you take a weight of some kind and hold it above your head for a long period of time, you start to get tired. But you're not really doing any physical work, yet you still get tired. So these metabolic processes which convert energy are going to play a role now. So make sure you try to distinguish those things. Finally, there's a long discussion in the text about this notion of temperature. Okay? Don't try to make this too complicated, particularly on the first pass. Okay? We're going to think about the kinetic energy, the average kinetic energy. In terms of the temperature. Temperature is a measure of the average kinetic energy. And for what we're going to be doing here, the average kinetic energy is going to be 3 times, and we're going to have this 1/2 K Boltzmann, which is a constant, times the temperature. You can think about this as a definition. You think about this as empirical. Actually, it has very, very deep roots in physics. But for our purposes, average kinetic energy reflects temperature, or vice versa. So when you measure the temperature of something, you're measuring its average kinetic energy. There are a lot of conceptual challenges here. We're going to see some new stuff. I really recommend you doing some of the questions at the end of the chapter. In this particular case, I would do problems 1 through 10, and then 28 through 30 are pretty good as well. So if you want to really try to test how firmly you grasp these ideas, do that. Okay. But as always, when you reach particularly tricky spots, come and try to talk about it.